And this is where we are going to start, looking at what we call as phasors. We had a basic stint at what phase is and how phase is defined, okay? And phase is essentially this, by convention, this cos omega t has zero phase. And in order for that convention to work along with all our mathematical identities intact, cos is along x-axis, sine is along y-axis, negative y-axis, right? That's sort of a mnemonic. Now, this is where we actually get to what we are referring to as phasors. So notice what we are going to do is we are going to forget this oscillation altogether in order to make easy calculations. Okay, we are concerned about what its peak is. We are concerned about what its phase is. And we are going to define something called a corresponding phasor, capital V of t. This is bold V of t. Okay, that has this notation. It has its peak and it has its phase as an angle. The reason to do this is this. Say in case of resistor circuits, say your voltage is like this, okay, pure resistor, your current is also along that. So if you know the instantaneous voltage, you also know the instantaneous current. If the voltage moves here, the current moves along that arrow. Okay, if the voltage moves here, current also moves along that arrow. The corresponding sine value or cosine value, can be traced from projection of this along the circle. Okay, this vertical projection is shown over here. See, at this instance, things are oscillating, so we are looking at it as a circle. Okay, if you look at its projection on the real axis, right, you get the corresponding function value. As this thing oscillates, say, notice the projection value decreases, okay, and goes further below, okay, then reaches its negative most peak, and then as it oscillates further, starts rising. Okay, starts rising. So this oscillation, it's very convenient to see that in a circle. It's repeating again and again. So circle is a very convenient place to see that. And again, notice if we have, if you're looking at a pure resistor, okay, if the voltage is like this, the current will also have the same phase. That is, current will be a scaled version of this curve. That scaling coefficient is, R. V is IR. Okay, so current is, notice, a scaled version of voltage. But give me V of t, well, voltage at any time, I get current at any time. Right? Problem is very, very simple if you're dealing with resistors. So we have voltage, the current will almost look a very scaled version based on the value of R. This will be either higher or lower, but the function will essentially look at high. But the moment you have a element like a capacitor, okay, if your voltage is like this, current won't be exactly, will have the same phase as the voltage. Current will have a slightly different phase. This is also the case for an inductor. Now, again, if you get to a convenient circle representation, what it means that for a resistor, if voltage is this, current is aligned along that direction. But for a capacitor, if voltage is this, current is aligned along some other direction. Let's say this. Let's call this angle alpha. Okay. What makes this phasor domain representation work is this. This particular alpha, that is voltage is vector is this, current vector is this. The difference between the two vectors, the phase difference between the two vectors, alpha is always a constant. That means, you know, at, you can completely forget that things are oscillating. Just give me voltage. With respect to voltage, I will tell you what the current is. That is, give me V of t at any time instant. I will tell you I of t slightly earlier or later. T plus, a phase. I can tell this. This relation is preserved for capacitors and inductors. So we are going to completely overlook what this omega t is. We'll be working with, okay, what is the voltage peak? That is, what is the magnitude of this vector? What is its current phase? Okay, that is with respect to a normal cosine. How does the voltage function look? If we know that, okay, we can start getting the current and things like that easily. Okay, current will be Im. Of course, it will have, it will depend on the phase voltage, but there will be a slight change in phase also. Okay, so phase difference alpha, the phase difference is a constant. So we will forget about oscillations. We'll only look at the peaks and phases. Phase difference, let's call this, is preserved. And what are the conditions under which it's preserved? As far as you are dealing with a capacitor and an inductor at a particular frequency. If omega is constant, you are varying omega, then voltage is kind of varying some way, then phase and all is not preserved. Okay, omega is a constant. Now let's look at, this, start looking at this complex numbers. We have something called a leading direction and a lagging direction. Okay, I already said counterclockwise direction is positive. Okay, so with respect to x-axis, something has a positive phase, that is known as a leading direction. Positive phase. Okay, and with respect to the x-axis, if things are in the negative phase, that is known as a lagging direction. Okay, what is shown here is the voltage vector and corresponding current vector for some element, whether it's a capacitor, inductor, combination of capacitor, inductor, we don't know, some combination, arbitrary combination. Okay, if the current is over here, it has a negative phase. The current is above voltage, it has a positive phase.